Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Let's go ahead and take a look at our writing the equation of a tangent line when we're given an implicit relation. Firstly, what's the dead giveaway that this is an implicit relation? Vivian?
X's and Y's on the same side.
Absolutely. We've got our X's and Y's mixed up on the same side. We're not solved for Y explicitly by itself as a formula, as a function of X. So let's go ahead and differentiate so that we can get our slope of the curve. We still need dy dx, right? The instantaneous rate of change in y with respect to x. It's just that every time we differentiate a term that includes y in it, we have to use the chain rule, right? We have to do times the derivative of the base, and that's where we get that dy dx from. All right, so we need the same three things that we've always needed for the equation of a tangent line. We need x sub 1, y sub 1, and our slope of the tangent line. It looks like in this implicit relation we're given 1, 2 out of 3 ain't bad, right? So let's go ahead and generate our expression for dy dx. So we'll differentiate term by term. The derivative of 2x with respect to x is 2x minus, and depending upon how you'd like to handle that product, right, you can use parentheses here, or you can break the group the negative with the x and call that a single term. I'm going to go ahead and do minus, and then I'm going to do the product rule on xy. The derivative of a product of two functions is the derivative of the first times the second plus the first times the derivative of the second. And here's our dy dx. End product now plus the derivative of y squared. Well, that's just power rule. Exponent times the base raised to 1 less than n times the derivative of the base, and there's our dy dx again. And the derivative of any constant is 0. So our general scheme then is to get rid of the parentheses, add or subtract to isolate the dy dx terms on one side, factor it out, and solve through division. So it looks to me like first I'll do a quick rewrite to get rid of the parentheses. Then I'll go ahead and add over the y, subtract over the 2x, reorder to make my factoring easier. Mess up the signs? We okay? We okay? Great. Factor first or fail. We'll go ahead and pull out that dy dx. Go guide north. And then we've got 2x, 2y.
Drop the y.
Right here?
Yeah.
Awesome. Thank goodness for you guys. So we've got our 2y, dy. So right here is 2y in green. Yes? Yay! And now we have 2y minus x equals y minus 2x. So close, and yet so far. All right, so we'll finish it out and get my expression for the slope of the curve anywhere along it. Looks like dy dx is given by y minus 2x all over 2y minus x. Raise your hand if you had this expression for dy dx. Great, thanks. And now we'll go ahead and evaluate it at our point of concern. We want to know what the slope of the tangent to the curve is at the point 2 comma negative 3. So I'll simply evaluate my dy dx, and I'll get negative 3 minus 2 times 2 all over 2 times negative 3 minus 2. Is that right? This is going to be a 1 or a negative 1. I'm sure it looks like it. No, that's negative 3 minus 4. That's negative 7. And this is 2 times negative 3 is negative 6 minus 2 is 8. No, negative 8. So it looks like we're getting a positive 7/8. So raise your hand if you had 7/8. Anybody have 7/8? 7/8? Great, let's put it all together, and what do we have? We've got y minus a negative 3 equals positive 7/8 times quantity x minus 2. Because I'm going to put in the grapher, I'll do y equals, and I'll leave this alone, 7/8 x minus 2, and then minus 3. Except, I didn't know how long our discussion was going to take, so I already put it in the grapher. It looks to me like we've got, there's our 0.87500000104. Doing the old college try. 0.875 is 7/8, right, as a decimal. And then minus 4.75. So that'd be 1, 2, 3, 4, 16, 19 fourths. Huh? Very nice. Hey, that was pretty good. So we know that this is really connected, but due to the limitations, right, on the pixels on the graphing calculator, and I had to solve this for y, enter it, right, explicitly in two separate functions, my top portion, my bottom portion. So that's why the different line styles are there. This should be connected, right? This should be connected as a single curve. Ooh. Thank goodness for that orient, huh? So that's what it really looks like. I kind of like these implicit relations with that xy product in the middle and that diagonal football. It kind of looks like a diagonal football. That's fun. What questions do you guys have about your bell work? So I want to see a thumb from everybody. This is how you're feeling with 1 day of implicit differentiation, because that's kind of all I was counting on. Because I know, yay! Hey, we can move right on then, right? We can move it, yeah. We're gonna keep on rocking. Okay, let's go ahead and give you credit for OTL number 3. I'll pause the recording. So, dun dun dun. Think back to our connection between a function and its first derivative, right? So, in general, if we have a given function y, we know that if that function y exhibits increasing behavior, what must be true about the values of y prime? Marissa?
Oh, gosh. Oh, they're, positive.
True that. So we've got positive y prime values indicate increasing behavior in y. Now, y prime doesn't have to be increase. We don't know if y prime is increasing or decreasing. We just know that it's positive, graphically above the x-axis. That indicates then that y is exhibiting increasing behavior. Well, to that end, right, what else can we tell? Sophia?
That when y is decreasing.
Okay, so if we have decreasing behavior in our original function y, then the values of y prime must be negative. Again, we don't know if y prime is increasing at this state or decreasing. We just know that the values are negative or beneath the x-axis graphically for y to be exhibiting decreasing behavior on the same interval. And then lastly, we were very careful about this. If the value of y prime was 0, that did not mean that y had a maximum or a minimum, only that y had a horizontal tangent for sure. It could be a maximum or a minimum, but for sure, if y prime had a value of 0, right, or an x-intercept graphically, we know then that y had a horizontal tangent at that same x value. So we'll go ahead and call that a horizontal tangent. Okay. So why the Think Back Monday, Mr. Fritz? Well, because today we're going to now cast our study of differentiation in the context of particle motion. So the same relationship that exists between a function and its derivative now we're going to examine in the context of particle motion now with position, velocity, and acceleration. So first, right, let's suppose that a falling object's velocity function is measured in feet per second. From that, we can infer what units the object's position function would have and what units the object's acceleration function would have. I'm going to call on you. Old news. So if our falling object's velocity is in feet per second, what units would position be in? Kobe? Feet. Thank you. What units would the acceleration function be in? Riley?
Feet per second.
Yeah. Oh, going back to the abbreviation now, aren't I? Because feet per second is a lot quicker to write like that. Okay. So why the big buildup? Well, because we want to make sure we're comfortable with our derivative hierarchy, our ladder. So I've got my infinite cloner here. Obviously, I spent the majority of Friday when I wasn't talking with Paris putting together for this one moment. Yes, that's right. Go, got your arm. So what's the derivative of what's the derivative of what? Right? How does this work, Courtney?
Velocity is the derivative of
Awesome. Raise your hand if you agree with Courtney's. There's our derivative ladder. Yes. So then in turn, if we were to spin our arrow upside down, we know that the derivative of position is velocity, right? And then if we were to differentiate velocity, we would get down to acceleration. We have to be comfortable going up and down the ladder. And we have to be comfortable going up and down the ladder. Today we're going to focus on the differentiation. Are we good? Did I mess up anything? I practice. I do like. Go ahead. Remember to do the go guys down first so I have space? You guys, no? Yeah. I get into this. All right. So today we're going to focus on the differentiation aspect. We're going to hold off on the integration, okay? And so what I want to do, even though you remember from AB when we talked about like total distance traveled, right? And displacement using integration, we're going to hold off on that and do it solely with, solely with differentiation. All right, so let's go ahead and draw some parallels between graphical behavior of y and y prime, and now cast in the context in the arena of particle motion. So we're going to go ahead and say that our position, our position is increasing, and that indicates, typically in these motion problems, that means moving to the right or up for our rectilinear motion. So we're going to now think more about this as moving to the right or up versus position decreasing. Now we're talking in particle motion about moving to the left or down. Awesome. So, yes, we need positive velocity values. That'll indicate that our position is increasing. But more importantly, now we're talking about moving to the right or moving up, depending on how we define our positive direction of motion. Negative velocity values will then indicate that our position will be decreasing. That is moving left or down, depending on how we defined our direction of motion. And then lastly, what's different here is if my velocity is 0, right? If my velocity is 0, then typically for us, that means that our particle has stopped, right? It's stopped, or it is what we call at rest in a lot of these application problems. So we'll say particle is stopped, not moving, or what we call at rest. It's a buzzword in some of these applications. So there's our connection between what we already know about y and y prime, and then now to position and velocity. Can we extend it one more? Yes, Courtney gave us our hierarchy, so we know then if velocity, if velocity is increasing, then we know our acceleration must have positive values. If acceleration has negative values, then we know our velocity must be decreasing. And now I'm going to go ahead and say for this one, if our acceleration is 0, then I'm going to go ahead and say a possible, We've got a possible maximum velocity attained. We care about that for particle motion. It doesn't mean there is, though, a possible extreme. So we'll go ahead and call that a possible extreme for velocity. The reason we're saying this different, the reason we're saying this differently than for our function behavior before, is that in these application problems we care about like when maximum velocity is reached or minimum velocity is reached. So a possible extreme for velocity. Can you guys fit it in little squares? Because I was trying to save a little bit of paper. I know it's tight strength. Okay. Ready? So then let's go ahead and remind yourself then, in order for our object to be speeding up, what has to be true, about the relationship between position, velocity, and acceleration. So in order for our particle to be speeding up, what has to be true about our relationship between position, velocity, and acceleration? You got it? You got it? You got it? You ready? You ready? Are you ready when I call you? I'm going to call you right now. So you're ready now to because the recording's on. Sydney.
So for speeding up, isn't it velocity and acceleration need to have the same sign?
Dang, yes. So V of t and A of t must have the same sign. That is both positive or both negative, right? So long as they're the same sign, we know that my particle is going to be speeding up. Why? Well, my velocity could be positive and getting more positive, right? Or it could be negative and getting more negative. Either way, the speed, the magnitude that is the velocity, would be increasing. Graphically, the distance of my velocity away from the x-axis, that magnitude would be increasing, that's speeding up. And so then we're slowing down, Vivian?
And they're opposite sides.
Yeah, when V of t and A of t have opposite signs. So graphically, my velocity function could be positive, right, but decreasing. That is getting closer to the x-axis x-axis with its values. Or my velocity function could be negative and increasing. It would also be getting closer to my x-axis, right? And the magnitude then would be decreasing as well. Either case indicates slowing down behavior. Awesome. So can we do some stuff? So we're going to try non-calculator. So we're going to try non-calculator today, and you guys already know all about your math 8s and your math 9s. So what we're going to do is today try to do non-calculator, and then we can bring that back in later. So the position of a particle, where t is measured in seconds and s in meters, is given by s equals f of t is my position function, is given by t cubed minus 6t squared plus 9t. The College Board just redid the AP curriculum in terms of practices, and so that what they've been doing is making an emphasis connecting multiple representations for notation for the same concept. So I painstakingly made s equals f of t so that we could go ahead and practice with our differing notations. Yes, that's right. If we were to differentiate my position function to generate velocity, we could call that ds dt. That would be equivalent to the first derivative of my position f prime of t, which with Euler notation then would simply be v of t. And so all that to make the connection between Leibniz notation versus our prime notation, and call it a new function v of t whose derivative, right, of position is velocity. All right, so what's that going to be given by? Tyler?
3t squared minus 12t plus 9.
All right. What's the velocity after 2 seconds and after 4 seconds? Again, we could call this ds dt, and then there's a little line here, evaluated at 2. That's the same as f prime of 2, which is the same as v of 2. I think we can do this in one line, can't we? So 2 squared, 4, 12 minus 24 is negative 12 plus 9 is negative 3. Are you guys getting negative 3? Yay! And what would the label on that be? So our label on that would be t is measured in seconds, s is in meters. So what would our label for that be, Kobe? Meters per second. Awesome. And all right, and we can do the same thing for 4 seconds, but I'm just going to jump down to right here and do it for 4. So 3 times 4 squared minus 12 times 4 plus 9. Oh gosh, we're trying non-calculator. So 4 squared is 16 times 3 is 48. Minus 48 is 0 plus 9 is 9. 9? Hey! That's not so bad. Anytime you guys want to add a little note to Emily or something, we'll put that down on the bottom. All right. So we're good with non-calculator. Calculate the derivative, evaluate velocity for given time values. What about when is the particle at rest? Right? So we know that in the scheme of things, our particle or object is at rest when what's true? Well, I'm searching and I'm not seeing, and I'm scouring our notes earlier. There's the key word. When we're at rest, what's true about our position, velocity, or acceleration? Sophia?
Velocity is zero.
Awesome. So let's take our velocity function, call it v of t, set it equal to 0 and solve. So we already have our 3t squared that Tyler can list out minus 12t plus 9. We know that that is equal to 0, that our particle is stopped or at rest. No problem here. I'm all about the factor versus trade-off. In fact, that's one of my favorite things to do. Got some new riddle worksheets from Khan Academy, so I've been doing that just to keep my skills sharp. Stand still, but we have resident expert factors in here, so that's good. So what did you get for this factorization, Grace?
T minus 3 and T minus 1.
Awesome, thanks. We can solve now for t by setting each individual factor equals 0 and solving separately. So it's like a particle is stopped at t equals 3 and t equals 1 second. So a particle is at rest at t equals 1 and t equals 3. Awesome. And t equals what? 3 seconds? Gosh, excruciating detail. I'm going to carpal tunnel if I'm not careful today. And d? When is the particle moving forward? Oh, so the particle is moving forward then what's true when what's true about position, velocity, or acceleration. So particle is moving forward when? Marissa?
Velocity is positive.
Velocity is positive. So we've already got our critical values. That's our potential values where we change direction. So we can simply go right to our v prime number line and do a sign test. Add our critical values, and this will give us a snapshot of the direction of motion. Remember this? Easy cheesy. So we've got 1 and 3 for our time values. And we're going to choose a convenient x value or t value on each subinterval and evaluate. And so a convenient value on the leftmost subinterval would be 0. Evaluate my velocity function, which I don't have anymore. Fine. So I'm really good at differentiating polynomials. I think you guys are too. Did I have this fully factored? I did have it fully factored. That was easier when it's fully factored. So can I do one more? I'm gonna do one more. 2 minus 1, 2 minus 3, guys. Alright. Now it's easy to do our sign test. In for t equals 0. Negative times negative overall is positive. 2 in for t. Positive, negative overall is negative. 4 in for t. Positive times positive overall is positive. Hey, when's the particle moving forward? All right, when's our particle moving forward? Danny?
0 to 1. Negative infinity to 1.
I'm with you. So if we didn't have a domain restriction, we could say negative infinity to 1. I'm guessing if it's in seconds, yeah, let's go 0 to 1. And let's go 3 to infinity is my guess. I need to include that in the future. Sorry, Danny, that's my fault. So moving forward. On 0 to 1 and 3 to infinity. Why am I not including 3 or 1 in my intervals? Well, my particle is not moving forward at t equals 3, right? What's the particle doing at t equals 3? We saw, right, we're stopped at t equals 3. And did I make another one for this? I did. And I wanted to add the strict requirement that we figure out the distance traveled, right? Only using derivative applications. So can we do that? Well, that's new and different. Last year we used integration to determine displacement or distance traveled. We integrated. So how are we going to do it with just differentiation and not integration? Well, we know when my particle is moving to the right. We know when the particle is moving to the left. And so if I can, and we know I have a position function. So if I can calculate, right, if I can simply figure out where my particle is at each of those key turning points and then add up the motion on the subsequent subintervals, then I'll get the overall distance traveled. So what do? I'll go ahead and make a t chart. Instead of an xy chart, I'll make a t f of t, that is a position chart. I'm going to go ahead and put on my endpoints of the overall interval, and then any critical x values. This is sounding familiar. Kind of like the closed interval method, right? But in the context of particle motion. So let's go ahead and put on endpoints of the interval. And this time I did give you something, Danny. What did we say? We said the first 5 seconds. So we can say 0, we can say 5. And are there any critical values? That is places where we have a potential change in direction? Yeah, at 1 and at 3. Now it'll be easy. All we'll do is we'll evaluate our position function at each of these time values and then sum, right, the respective changes in position such that each change in position counts as a positive contribution towards my overall distance traveled. So let's go ahead and do that. When t equals 0, position is 0. When t equals 1, position is 1 minus 6 is negative 5 plus 9 is 4. Are you guys getting 4? 4. When t is 3, 27 minus 6 times 9 is 54. Is negative 27 plus 27 is 0 again. You guys getting 0? I guess you're on this like calculator. You guys are fast. 5. Oh, 125 minus 25 times 6 is $1.50. So minus 25 plus 45 is 20. You get 20? Sydney? Sorry, this is Kobe, that's what I do. 20? Yes? Awesome. So what do we do now? Well, clearly I had change in position. We already saw my particle is moving to the right on 0 to 3, to the left on 1 to 3, and then forever to the right after that. So what are we going to do here? Well, we can take into account our net change here. So what do? We move 4 meters. From here to here, we moved another 4 meters. And from here to here, we moved 20 meters. For a whopping total of how many units? 4, 4, 8, 20, 28, 28, 28. So we moved 28 meters. And now is a good time because I have some space. So it looks like 28 meters was the total distance traveled in the first 5 seconds. Awesome. Okay, so how'd that go without a calculator? Okay without a calculator? Great. Now let's go ahead and step away from the symbolic algebraic manipulation, and let's go ahead and include our graphical connections. So now, all right, now let's go ahead and just focus solely on graphical behavior and see if we can answer some similar particle motion questions. Consider the given graph based on an object's motion on the time interval 0 to 10 seconds. When is the object moving to the right? Well, I know my object's moving to the right when velocity is positive, right? Because we filled out our little chart to remind us. The thing is that you have to be careful what we're looking at. What function's graph are we looking at here? Danny?
The position.
Yeah, we're looking at position. Right? We're looking at position. And so this isn't the plain Jane question we're used to seeing, right? Where we're looking at a velocity graph and seeing where it's positive to indicate where my particle is moving to the right. Instead, we're looking for what on this graph? Go ahead and tell your partner. Right? How are we going to tell when our particle is moving to the right? So what are we looking for on this graph? Go ahead and tell the whole class, Grace and Sophia.
Positive slope.
Positive slope on the position function would indicate increasing position. That would be moving to the right, and positive velocity all at once. And so what subinterval did you say, Grace?
When t is greater than 6 and less than 8.
Absolutely. So in interval notation, that would be 6 to 8. And again, I'm going to put parentheses there, right? Exclusive, because it looks like we've got this change in direction here, and we've got this corner kink cusp, and so we're going to go ahead and exclude that from our subinterval. Sydney?
So like if it wasn't, did you say exclusive?
Yes.
This is exclusive?
Yes.
If it wasn't that, you'd use brackets, right, if we included.
For interval notation, yes. Yes, good. When's the object at rest? Go ahead and tell your partner. Based on a position graph, can we see that when it's at rest? I can see when my position is positive, negative, 0, but what about at rest? So what now? Marissa and Brendan?
Slope is at 0.
When slope is 0, and so do we attain that on this graph? Yeah, so if we're 0 to 10 only, so what interval is that? Can I count this one? So 8 to 10? 8 to 10? You guys good? Okay. Oh boy. Did you guys see that? You guys want to include those?
No.
Okay. We okay?
Yes.
When is the object speeding up? When's the object speeding up? What? From this graph, can we tell when the object is speeding up? We're looking at position. What? All right, so how might we be able to tell if the object is speeding up? Cody?
That would be when it's curved. You're looking for curvature.
Curvature on the position graph. And as I look at this, do I have any curvature? So is my object ever speeding up? It looks like it changes direction, right? But we don't have any horizontal tangents. We just have corners or cusps or kinks. So is it impossible to tell? Well, what would we need? We would need what Sydney told us. We'd need velocity and acceleration to be the same sign, right? We need it to be the same sign. And so we would need our slope of this to be positive, right? The slope of position to be positive, and concave up, right? Or we would need the slope of this to be negative and concave down. And because we don't have any curvature, right, is my particle ever speeding up? No. And so we can't say that. So what would be a reason for not applicable? I probably should say never. I shouldn't say not applicable. We're always applicable, right? There's so many application days. Oh. How can we reason that out with calculus? What is the acceleration of my particle anywhere along here? 0, right? If I could have velocity that's positive, I can have velocity that's negative, but the derivative of these, right, of the velocity function, because it's a line segment, would be 0 in each case. So acceleration is 0 throughout, or undefined throughout. But it's not positive or negative, so we can't have the same sign as position. Oh, dirty dog, watch where that lands. So we can't have velocity acceleration be the same sign if, right, our acceleration is always 0 or undefined. When is the object going the fastest? Now can we answer this question? right? When is the object going the fastest? We're looking at position. All right, who thinks they have it? Anyone? No? Two's up to team? Cody?
The slope is steepest.
Because velocity represents the slope of position. So when the magnitude of the slope on this graph is the largest, then it will be going the fastest. So we can again zero in on this, what, 6 to 8 is the steepest part. And it could be negative if it were steeper there, but it looks like steepest is up 2 over 1, so that's what I was going for. Awesome. So it looks like 6 to 8 seconds. Awesome. Nice work. Questions about our position graph? And I swear this is a brand new object. You might be thinking that graph is similar. To which I would reply, nice try. Look at the vertical axis. Yeah, so now we're looking at which function, right? Which function we're looking at now? Tyler?
Velocity.
Velocity function. And we're going to ask the same kinds of questions. When is the object moving to the right, right? So when is the object moving to the right now that I'm looking at a velocity function? Well, now it's back to our radar scheme, right? Riley?
Be when velocity is positive.
So that is, nice job. 0 to 2 because velocity is positive. I like including a justification response. Riley? Dang. What's on my team? When is the object at rest? Right. So when is my object at rest? Courtney?
2 seconds. And then.
Absolutely. When my velocity is 0, my particle is at rest. And so at t equals, I'm supposed to get you can see I've been tweeting for a while. So t equals 2 and 8 to 10. And v of t would equal 0 at those places. So my particle would be at rest. Old news, easy cheesy. What about when is the object speeding up? When is my object speeding up? That's even better. I like math. Don't worry, buck up, little partner. Things will go your way. It's not as bad as they seem. Sydney, it'll be okay. So when is our object speeding up then, right? So when on this graph would indicate speeding up behavior? Tell your partner. When is speeding up there? What? Can we do this? I think we can. So, I heard some good conversation over here. Courtney, what are you guys saying?
We said 2 seconds through 6 seconds because it is both negative and on your x-axis.
Awesome, because what is both negative?
Both velocity and acceleration.
Good. And so it looks to me like on the time interval 2 to 6 only, right? Then my particle is speeding up. Raise your hand if you had that 2 to 6. 2 to 6. Okay, and so our justification, we're looking for velocity negative, right? Velocity negative and the slope of velocity, which would be acceleration, also negative. So we need negative velocity values and decreasing behavior velocity, right, on the same part of the graph, versus increasing velocity, right, but negative values is no good. We would need increasing positive velocities in order to get speeding up, and that doesn't happen anywhere on the graph. So our only interval here, right, is negative velocity that's also decreasing. That's on 2 to 6. Nice job. That was pretty sweet. So we need v of t to be negative, and I'll call it decreasing since we're looking at a velocity graph. Velocity graph to be decreasing for acceleration to be negative also. When is the object going the fastest? Can we do this? When is the object going the fastest? So what do you think about that? Kobe?
6 seconds.
How come?
That's when the velocity is furthest from the x-axis.
Absolutely. So the magnitude of velocity, even though negative, is greatest at t equals 6 seconds because speed is the absolute value of velocity. So I'll go ahead and just throw that on here just for good measure. Speed equals the absolute value of velocity. So at t equals 1, 2, 3, 4, 5, 6, the magnitude of velocity is the greatest. And I swear this is a brand new object. Brand new object. I know you might be thinking that graph is worn out now, but suddenly it's a brand new problem when we have acceleration function now. So not position, not velocity. And can we answer some similar questions? When is the object traveling at a constant rate? So when is the object traveling at a constant rate? Go ahead and tell your partner, be ready to share.
Yeah.
Do we have enough information? NEI? Not enough information? What do you think, Riley and Vivian?
When acceleration is 0.
What is, okay.
T equals 2 and then
Yeah, this is an interesting one. So I'm going to agree with you. We know that velocity would be constant, right? Velocity would be constant when acceleration equals 0, because then in the instantaneous rate of change in velocity with respect to time would be 0, which means velocity wouldn't be changing, so it would be constant. So at t equals 2. It's just that here, right, it would be at the instant when t equals 2, because velocity is neither increasing nor decreasing, and if it's neither increasing nor decreasing, then it must be, right, it must be constant. And so we're going to go ahead and say at t equals 2, and 8 to 10. Why? Because a of t is 0. Very nice. When is the object's velocity at a maximum? When is the object's velocity at a maximum? Go ahead and tell your partner. NEI? Is NEI better or worse than TMI? NEI? Bless you. Cut it. All right. Does anybody have it?
Yes.
Sydney?
Is it at 8?
At 8? Because
Like that area that's the biggest under the curve.
only differentiation.
Oh.
No, I mean, or whatever. Or whatever you want. But wait, we want object velocity to be at a maximum.
Absolute value.
Oh, and not speed.
Oh. So would it be at 2 then?
Why at 2?
Because that's when the, wait, so no integration? Or,
You can do it without integration.
wait, so can I do the area above the curve or no?
I will say at t equals 2 is correct. But then I'll ask you, how come?
Can I say that the area above the curve, that's like one of the biggest?
Yeah, but I don't know if we have to, right? No.
Or it changes signs right there?
What changes sign?
The acceleration,
Right, which is what of velocity?
the derivative.
Good. So if acceleration, right, switches from positive to negative, that would indicate a maximum value. And we weren't asking about speed here specifically, right? We weren't asking about speed. We were asking about velocity, and so we were talking about greatest value of velocity. That has to occur when acceleration switches from positive to negative. Good job. So we'll go ahead and say that equals 2. And we'll also add because v prime equals a of t switches from positive to negative. All right. Okay, and we're close. So let's go ahead and sum it up for today. And I think I gave you, yep, I covered you a couple space. And so we've got 3 whopping slides, but I wanted to do this for our note sheet so we had enough space. So what must be true about an object's position, velocity, or acceleration in order for the particle to be moving to left down, at rest, speeding up, slowing down, reach a maximum velocity, reach a minimum velocity, and then going the fastest. I think that'll do it. Okay. Okay, what must be true about position s of t and or velocity v of t and or acceleration a of t in order for my particle to be moving to the left or down? Vivian?
S of t would be decreasing, v of t is negative.
Awesome. So s of t decreasing and v of t negative. Excellent. What about at rest? Right? What about at rest? Sydney?
It says v of t equals 0.
And I'm sorry about the printing. What if for my particle to be speeding up? Sydney told us that before, right? So for speeding up, Brendan?
Same signs.
On?
V of t.
Good. So V of t and A of t must have the same signs. I'm sorry that I didn't print out with our answer very well. And slowing down then? Slowing down, Sophia?
V of t and A of t have opposite.
Thank you. That's what it's supposed to say for 3 and 4, but I know you guys have 5, 6, and 7. So in order to reach a maximum velocity, we just got to this at the tail end. So in order to reach a maximum velocity, right, what must be true about position, velocity, acceleration, etc. So what about that? Danny?
Acceleration switches from positive to negative.
Good. A of t must switch signs from positive to negative. So A of t must switch from positive to negative. Good. So to reach a minimum velocity, right? For minimum velocity, then what must be true? Marissa?
A of t switches from negative.
Good. Close. And for a object to be going the fastest, what are we looking for? So for the object to be going the fastest, then what are we looking for? Kobe?
When v of t is furthest from the x-axis.
Yeah, when the magnitude of B of t is at a greatest, is at the greatest. And so I'll go ahead and maybe call it absolute value of velocity is largest, maybe. So whether graphically, we're talking about graphically my velocity function being farthest away from the x-axis, right? That would indicate fastest speed, either positive or negative. Nice job, you guys. What questions do you guys have about our particle motion applications? Great. Then our OTL includes a mixture of even and odds. What I've done is I'm going to put the even ones. So I try to pick out a lot of odds, but there are some good questions that were evens, by golly. So I want to include those even ones anyhow, and I'll work to get that OTL up. And you have a nice chunk of time now, it looks like, to work on this too. And then I'll go ahead and pause the recording and upload it. And then you guys can use this time to work on your OTL 4.